Critical flaw size indications and inspection reality, Module 5. Gary Pace, PE, welding engineer.
All right, so we're going to talk about limitations in flaw size because none of these non-destructive testing methods is perfect and can pick up every last imperfection or discontinuity. So there are limitations. It's kind of like eyesight or something. You know, there's limitations on what you can see at certain distances, and these non-destructive testing processes also have limitations on what they can pick up. What's the limitation in the flaw size that they can find? So determination of the limitation of the flaw size isn't always an easy thing to get figured out. This is something that's got to be figured out and determined, and there's got to be some thought that's put into it. Once again, this isn't an easy thing to figure out. One common limitation specified in the use of NDT is no flaws are allowed. And this is just completely insane because within any material there is going to be a flaw or some kind of discontinuity. It's just getting to the point to where we as engineers and material science people and inspection technical individuals can understand what those limitations are. And we need to realize what we can live with and what we can't. So even though we'd like to have no flaws, nothing's perfect in this world. And we need to understand what is the limitations of these processes that we can live with. So no inspection or test method is going to be able to find every last flaw in a piece of material. So with limitations in flaw size, we've got to realize that it's impossible. There's some things that are impossibilities, like find all flaws or find the smallest flaw possible. Well, what does that mean? And then once we figure that out, we're going to figure out, oh man, this is going to be super expensive. Non-destructive testing is very expensive. You can make or break a job depending on how much NDE you're going to have to do. So even though we'd like to be able to find the smallest flaw possible, is it really important for everything that we're going to construct or build to just have everything absolutely perfect? Or can we live with certain flaws that are going to be inherent in that structure?
So zero defects is usually not super realistic unless you've just got ungodly sums of money and are in some kind of NASA situation. Because most manufactured materials that we're going to come across are going to have some kind of small imperfections. It's just the way the world works. And when it boils down to it, a lot of these discontinuities aren't really going to affect our performance once we get something into service. And then, if we're going to go out there and look for really small flaws, the inspection cost is going to go up because we're looking for needles in a haystack. So the bottom line is not every indication that we run across is a rejectable defect. It's a flaw, it's an imperfection, but it's not a rejectable defect. It's not going to do anything in regards to affecting that component to do its job.
So here's, let's have a little philosophical conversation. Here we're using, ultrasound, and we've got this big chunk of porosity down there, a big void. Well, can we live with that? This process, non-destructive testing process, is going to be able to find that a big flaw. Well, and then the designers and the engineers are going to have to calculate, hey, can we live with that, or is that going to be a rejectable defect? Or, here we've got some more porosity, but these are just little voids. Once again, can we live with this? We found it. Is it a flaw? Is it a defect? Or is it just a discontinuity that isn't going to have any overall impact on the strength of the material that we're using, the strength of the component? Is it going to be detrimental to what we're trying to do? And then taking it one step further, okay, we've got one little pore, one little bubble, one little piece of porosity, one little void down in there in this big block of material. Well, is that even count? And that's what the non-destructive engineers, testing engineers, and the structural and design engineers. That's their job, is to tell us, if we can live with this, and maybe we can't even find it. Maybe after a certain size, on going smaller and smaller and smaller, it might be there, but we might not even be able to find it. So these are some of the things that we need to keep in mind when we're talking about critical flaw size. So for every place NDT is going to be specified in the manufacturing process, we need to also understand that the important factors that need to be stipulated is the critical flaw size limitations. That must be detectable. Okay. Can we find this even if we use this process? And then almost all materials, as I've stated before, and all items made of any kind of material have imperfections of one size or another. It's just the way things are working. It's the way our universe is. Something's going to have a flaw. There's very little that is absolutely perfect. So when we have these imperfections, we need to understand, are they a flaw or are they just an imperfection? And a lot of times the very small imperfections or flaws don't necessarily preclude that piece of material from being used or being a useful item. So we need to understand this. We kind of have to get this ingrained in our train of thought when we start getting into NDE, non-destructive examination.
So why does critical flaw size matter? Why do we even care? Well, there's some codes, like structural steel, you can get away with having porosity up to a certain amount of little bubbles in the metal, right? In the weld metal. You can have a little bit of porosity. It's not the end of the world. It's probably not going to cause that thing to crash down. Whereas if we get into pipelines where we're trying to keep things inside the pipe, we really don't want little bubbles or routes that the fluid could, use to get out. So this gets back to a flaw might be acceptable in one application, but could be rejectable in another. Pressure vessels, pipelines, aerospace, they all use different acceptance criteria. A pipeline is not going to have the same acceptance and rejection criteria that something that's going on an airplane or a rocket or whatever. And the material thickness and loading conditions are going to affect the allowable flaw size. Let's say we've got a big casting, maybe the wall on this casting is 8 inches thick. And, we've got a little bit of porosity inside there, or maybe whatever our defect is. Well, that thing's such a beast in our loading conditions, it might not affect it. We can probably get away with some things there that we couldn't get away with on something aerospace that's really thin and light, and we need it to be near perfection. So the engineers are going to figure out the acceptance limits, and they're going to do this with code requirements, design analysis, and all that engineer stuff engineers do.
So sometimes it's going to be inefficient to inspect for non-critical flaws. Why are we even looking at this if we know there's going to be non-critical flaws in there? Why are we tying up time, man hours, resources, and money? So the engineers, the design engineers, the non-destructive testing engineers, really need to lay out, and a lot of the codes are going to do this for you, but they're going to give you a critical flaw size. And they're going to lay it out for you and give you guidance on what is a critical flaw. What is that critical flaw size? So those imperfections or flaws that are critical or larger than the acceptable are called defects. So this is where we go from discontinuity, flaw, imperfection into defect. It is impossible to determine the flaw limitations required for an inspection without knowing the purpose of the inspection as well as the complete design requirements of the finished part. So once again, this gets back to the designers and uh, the non-destructive testing engineers, giving the person on the floor guidance on what, hey, this is rejectable. This is something that we don't have to worry about. So, like anything else in life, if there's no paperwork, it wasn't done, right? So, a lot of times we're going to need to provide, you know, data, a test record for the testing that we've done. And usually, depending on what type of testing was done, there'll be some kind of evaluation sheet that is provided by the non-destructive testing personnel that says, hey, we did this test, this is what we found, this is what we didn't found, this is rejectable, this isn't rejectable. With x-rays, it's a little easier because with an x-ray, you've got the x-ray film, and the film will show you, it's like you broke your leg, and the doctor shows you, yeah, you broke your leg right here. We're going to put pins in your leg or whatever. Um, that would be an example of a record. Um, not every NDE test method provides results in terms of a permanent record. So sometimes, especially in the modern day, we're going to use like a cell phone or a digital camera to take a picture and then provide the end user with the results of that test. All right, here's your dye penetrant test. You can see we had a crack right here. This is what you need to remove. Blah blah blah. Here's the write up, and here's how we're going to do it. Or maybe it's good. They take a picture, nothing, everything was good, and we've got documented proof of the passing of the test. A lot of times, you need to understand that there's limitations with each test method, and this should be considered before we start asking for a lot of paperwork, because each process is going to have its own specific documentation and permanent record or documented proof that the test either passed or failed.
So NDE indications, we've got to interpret these things correctly because not every indication is a defect, right? And some indications, they might be geometric or process related. They're just in there because. And then we can get what are known as false indications during inspection. So we've really got to be able to interpret this stuff. And this stuff comes up in my worldview. Ultrasonic testing maybe a little more than others because you're reading what's going on in there and you have to make an interpretation. So this is why we have things like ASNT TC1A and inspector training and experience, limitations on how little they can have, what's the minimum amount of training they can have before we turn them loose to start making some of these calls. And a lot of times if we've got evaluation standards, that's going to help with our acceptability. And some examples, rounded porosity indications, what's it really going in there? Maybe we have a linear crack indication. Maybe it looks like a linear crack, but it's not really. And we got to interpret that, hey, this is just an indication. It's not really a crack. And in UT, you've got all kinds of weird reflectors and you're bouncing sound into solid parts. And, it takes a high degree of skill and training to be a UT technician versus a technician for ultrasound or mag particle, visual, or dye penetrant. So then we get into POD, probability of detection. And this tells us how reliable an inspection method is going to be when we start looking for flaws. It's going to be easier to find larger flaws. Small flaws, we might not be able to find them under a certain size. And What's going to affect our abilities here? Equipment, our calibration, and our operator skill. Probability of detection. This is going to help bolster our ability to evaluate reliability and limitations in regards to what we've got going on. So POD, it's how we measure the reliability of an inspection method. Hey, can this inspection method find this really tiny flaw? And if it can, what percentage of the time can it find it? Or what is our flaw size that we can find 90% of the time with this process? Questions, comments, thoughts, concerns? Gary A. Pace, PE, welding engineer, Katy, Texas.